Hello, I'm Ivan Fedianin. I'm software architect. I'm doing series of videos about distributed systems, and recently I have published several videos about leader-follower replication. So we have covered some basics, key idea of leader-follower replication, topologies, types of followers, trade-offs in different systems. In the second video, we have covered how to organize replication streams and how to capture data changes. So we could use statement-based replication, logical replication, wall-based replication, or trigger replication. It was not actually very tightly coupled with leader-follower replication because this topic can be used with any kind of replication. But anyway, in this video, we will dive even deeper. We know that when something is replicated, we have to worry about consistency. And we know several consistency models, and we will see how exactly we can achieve those consistency models with the leader-follower replication model. This video will be based on my article published on my website fedianin.com. It will cover all of it, but the videos will be split into several parts because this article is quite long and covers multiple topics. And here I'll show you what we will cover. So first, in this video, we will actually cover just problem statement and some nuances of implementations of leader-follower systems, which can affect how we can achieve different consistency models. Sometimes those consistency models are still achievable, but we need to make some fine-tuning of the systems in order to achieve them, and it is necessary to understand why we need to do it at all. Because in theory it looks very simple, you just have leader, follower, followers can be synchronous or asynchronous, so sounds very easy. But when it comes to real implementation, then it starts to become very interesting and nuanced. So we will cover, for example, how there could be some delayed visibility in reads even with synchronous followers or even out of order writes. So next we will cover eventual consistency, and we will see how to achieve it, and we'll consider kind of a real example which we could build based on the eventual consistency, and we'll see its limitations and some specifics which are made that way, especially because it's based on top of eventually consistent systems. Next, we will go to consistent prefix read and session guarantees, and as well there will be given some examples of some systems based on those consistency guarantees, of course applied to leader-follower replication system. Next, we will look at some example of causal consistency on top of leader-follower system. And sequential consistency in leader-follower system is usually achieved when we have kind of sharding and have a single leader per shard. And then we will cover linearizability, and then we discuss some problems why it can't be achieved or why it hardly can be achieved. Then we check linearizability and also consider transactions, and if linearizability makes sense together with transactions, and in fact it's not always making sense with them, and we need to operate with some other terms like external consistency or strict serializability, which is basically linearizability with transactions. And that's basically it. So this video will be split into several parts, but you can always refer to the main document, which link will be in the description of the video, just to check any specific point. I hope it will be easier to understand, and probably it's best to first watch the video and then check some specific points in the article to get deeper understanding or just remember some specific points. So let's start. First, we will start with replication lag, which is very important in replication. So the question is visibility of writes. When a client makes a write on leader and then immediately reads it back from the follower, so will the client receive that write or not? It's obvious that with asynchronous followers, a client has a high chance not to receive back the write if a client immediately reads it after write, because asynchronous followers by default they have some delay between write happened on the leader and this write arrived to the follower. Could we use just synchronous follower to eliminate problem with those delayed writes at all? Well, obvious answer is yes. From theory, we know that synchronous followers are the ones which will send acknowledgement to client only after the write was propagated to follower. And from a theory perspective, yes. But if we look deeper in the implementation, it becomes more interesting. So it appears that not in all cases, even with synchronous followers, the writes will be visible immediately. And because we are talking about specific implementation, let's look at some specific database system. In our case, we will illustrate it based on Postgres. In Postgres, replication happens by shipping val records. Just to remind, the val or write ahead log, those are records written on commit before actual data are written on disk. And using this write ahead log, even if power or even if server crashes, we can just replay them and restore the data. And in application to replication, we just ship those write ahead logs from leader to follower, apply them there, and on follower we get the state the same as on leader, because write ahead logs, they kind of say which bytes we need to change in order to get our target state of data. And so we see that there is a parameter called synchronous commit, and it can have 5 different values. So let's see why there are so many. On this picture, it kind of illustrates what happens with the data when they are committed on leader and how they appear on followers. For now, just ignore those labels on yellow background and just let's look at the replication process, and then we will get back to them. So let's see what's on that picture. Left side is a leader node and the right side is follower node. It's mentioned that the leader is, this block is called leader, but in fact everything on the left side related to leader and physically happens on the leader node, and everything on the right side is related to follower. When client commits some data on leader, first write ahead logs are written to wall buffer in memory. Secondly, they are flashed to file system, and then process called wall sender sends them to follower, and there the logs are processed by a wall receiver process. They are stored on file system, they are written to file system, flashed, and then one by one applied on follower. And when they are applied, only after that the changes are visible on follower. And the point of different values of the synchronous commit parameter of those values is just the point at which acknowledgement is sent to client. So basically, when synchronous commit is off, then acknowledgement is sent to client when write ahead log records are written to wall buffer. So it is in memory structure, and if they are written and, for example, server crashes, then acknowledged writes will be lost forever. So we are not even speaking about any replication here in case of crash. In order to guarantee durability, we need at least to flush those records to file system. And when synchronous commit parameter is set to local, it means that before acknowledgement the write to client, the system will ensure that those records will be flushed to disk. Now, if crash happens, those changes can be restored by replaying write-ahead logs, but at this point they are not yet sent to follower. So it means that if leader crashes, but followers are available, those data still will not be available. Next, while processes the logs, they are received by while receiver and written to file system buffer. This corresponds to synchronous commit value remote write. If it's set to this value, then at this point, leader will acknowledge the write to client. And what happens here? It's stored to file system. So if Postgres process crashes, the changes will not be lost because they are managed by file system and will eventually be flushed on disk. But if file system crashes, the physical machine or operation system, then in that case, changes will not be durable and they might never end up on the disk. Next value is synchronous commit on. It means that write-ahead log records were flushed actually to file system synchronously, and only after the flush, the acknowledgement will be sent by the leader to client. Now it means that even everything crashes after the acknowledgement, leader and synchronous followers, they will have all the data on their disk to restore those data. And only after write-ahead logs records are flushed to file system, only after that they are applied. Because remember, write-ahead log records, they are not yet data. They just log records which say how to build incrementally the target state, which is data. And it means that when they are applied, they become data state. And only after that, if client reads them from follower, client will see what it has written to leader. In the context of replication and consistency, it's important for us the visibility and replication lag. So we can see that only in case synchronous commit is set to remote apply, only in that case we will get immediate visibility. So after leader acknowledges the write, it will be immediately visible on follower only if synchronous commit is set to remote apply. And if it's set to any other value, then we will not get that immediate visibility. And by default, synchronous commit on Postgres is set to value on. It means that by default, if you write something on the leader, you don't have guarantee that you will get it back from follower immediately. That's the important point. One might ask why there are so many of those parameters and why don't just have remote apply, for example, by default and have the only value, why to overcomplicate? And the question, because actually it depends on what we want in each real specific system. We can see that number of actions are needed to be done in the system before acknowledge the write. It depends on the synchronous commit value. So, for example, this action is the fastest one. So it means that client requests will be processed very fast with synchronous commit is off. It will take a bit more time with local value. And for example, with the remote apply, it will take the longest time. It means that clients will have to wait a long time. They will have a big latency, big response time when writing something to the leader. And sometimes immediate visibility is not important, but the latency is important for some clients, for some systems. Because of this, real systems, they just provide a choice and it's their user developer, architect, engineer who needs to understand how it works and how to make the proper choice. So to conclude this section, I want you to understand that first, immediate visibility is possible. Second, it might not happen by default, even with synchronous followers. And thirdly, in order for it to happen, the system should be configured properly, and it will most likely cause longer response times of the server. So now we have understanding about visibility. Let's go to another interesting topic, which is called out-of-order writes. So when we made several writes one after the other on the leader, will they become visible on followers in the same order or not? It depends. Let's first consider asynchronous followers because they offer weaker guarantees in general. So we have leader, and usually leader can have multiple clients, and it allows parallel writes. And within itself, leader, it's a responsibility to establish the total order of all writes. So basically it accepts all of those parallel writes and establish some specific fixed order of all of those writes when it's writing it to its database. But how to ship all of those writes to asynchronous follower? If we want to ensure that all of those writes become visible on follower in exactly the same order they are linearized on leader, then we would need to have a single thread on follower which applies all writes. And in that case, they would follow the same strict order as on the leader. But this single thread, it could be a bottleneck in our performance because leader is multi-threaded and it accepts multiple writes, but single-threaded follower, it simply might not be able to cope with all of that load, and it could lag too much behind the leader. And in order to solve this performance problem, parallel replication is used to transfer data from leader to asynchronous follower. And with parallel replication, we might get out-of-order writes, because a write which was in some specific order was on leader before the other write, it might become visible after that initial write, and we might make out-of-order read. So first we will see one write, and only after that another write will be received. Of course, it's possible to make some synchronizations, implement some mechanism in order to ensure that writes are applied on the same order in follower, but of course such mechanism has some cost in performance. And for example, MariaDB has two modes which are specified in its documentation for parallel replication. If parallel replication is enabled, then it can behave with two different modes, in order and out of order mode. With in order mode, it's guaranteed that all writes appear in the same order they are applied on the leader. And out of order allows writes to be applied in different order. Of course, out of order method is more performant than in order, but it's a matter of choice. So for asynchronous followers, it's more or less clear. But what about synchronous followers? Because we know that by definition, synchronous follower acknowledges the write only after it was replicated to follower. So in that case, can we have any problem with out-of-order writes? And the answer is yes, potentially it's possible, and let's see the mechanism. So we see it on the example of MySQL in semi-synchronous mode. In semi-synchronous mode, it just means basically that one follower is synchronous and other followers are asynchronous. But let's consider synchronous follower. So we have a leader, we have a binary log, and this binary log is synchronously transferred to follower. and the client gets acknowledgement of the operation only after follower explicitly confirmed that bin log related to that operation was replicated. So that part happens synchronously. But then, after synchronous follower accepted the bin log, it does not mean that it will be visible immediately. And here it could be parallel apply when this bin log is applied just in several threads. And thus we can end up in having writes received out of order. This is configurable. MySQL provides two parameters specific to this. It's replica preserve commit order and replica parallel type. And it's possible to configure MySQL in that way that all writes are applied in order. To do this, you need to understand how it works and know that we need to configure it. So as a summary of this specific section, I want you to understand that even with synchronous replication, out of order writes are possible, and in order to avoid them, we need to carefully read documentation of our database system and configure it in case we really need it. And we should understand that there will be performance implications. So that's it for this video, and in the next video we will cover specific consistency models and how we can achieve them in leader-follower replication, and in what system and in what use cases we could use leader-follower replication with specific consistency models. In the next video we will review eventual consistency. See you!